Hello all. In today's session, let me learn about the topic which is programmable logic devices. So these programmable logic devices are used to implement your Boolean functions or your combinational Boolean functions using your PLDs. So hence these are all called as combinational programmable logic device, and these are available on an integrated circuits which can implement your the Boolean functions which are in standard SOP or in the simplified expression using your an array of your AND gates as well as your OR gates. So these PLDs can be programmable. So hence, so any designs can be derived from these PLDs. So hence we can achieve more flexibility if you use your PLDs for implementing your Boolean functions, and you can also perform the experiments in order to implement your n number of functions with use of these PLDs. So next, so few advantages we have it. So when I compare with your conventional logical gates utilization for implementing your Boolean functions using these PLDs. So since these inputs as well as your outputs are programmable, so we can reduce the space requirement as well as we can also reduce the power requirement, and the design security is available in your PLDs, so compact securities. So then we can develop these function many n number of functions using your less cost. So on your less cost, so we can achieve your more speed. So along with that, so in order to design your large quantities of the same product, same unit, so in your industry, so we're going to use this type of technique for reducing your cost of production. So we are going to prefer these programmable devices for implementing your the multiple n number or your n number of Boolean functions which are in all the form. So which are in standard form or in the minimal forms also we can represent using your programmable logical devices. Now classification of VLDs, basically these are categorized into based on your arrays of your AND as well as your arrays of your OR. So inputs of AND programmability or inputs of your OR programmability, so are fixed arrays of your and fixed arrays of your OR. So these are classified into three categories. First one is PROM, second one is your PAL, and third one is your PLA. So PROM is a programmable read-only memory. So as we discussed in the last class, so only once it is programmed, so that will be a programmable read-only memory. Whereas here the AND gates are fixed, so we are going to have your minterms using the decoder in your programmable read-only memory, and only the OR array is programmable. So the inputs which are connected to your OR gates are programmable. So you're not connecting directly from your outputs of your AND gates as the inputs to the OR gates. So using the fusible links, we were going to connect your output of your or the minterms which is obtained from your decoder to the inputs of your OR gates. So that will be your PROM. So PROM is having fixed AND array and or programmable OR array. PAL is a programmable array logic. So in this programmable array logic, inputs of your AND gates are all connected with the programmable fuses or the links, and your OR gates are fixed. In PLA, so where it is abbreviated as programmable logic array, so both arrays of AND as well as your OR arrays are programmable. So now let me deal with in today's session PLA. After this PLA, we'll move to your PAL. As we finish your PROM, so we will move to your PLA. So now this is the basic block diagram of your all these combinational PLDs, three categories. Programmable read-only memory, inputs are transferred through your fixed AND array. So where you are going to use the decoders, and that output of your each AND gates are connected through the fuses to the inputs of your OR array, where these OR arrays are programmable and the outputs are obtained from the programmable OR array. So hence it is fused programmable OR array. So it is available at your PROM. So whereas in programmable logic array, so you are going to transfer your inputs through the fuses to the AND gates or AND array, and you don't have your minterms. So based on your required product term, you can program your AND gates, and we can obtain your put the specific AND gates or the AND functionality from this programmable AND array. And here in PLA, so your OR gate is also OR gate inputs also programmable. So both AND array and OR array are programmable devices. So inputs are transferred through your programmable fuses as the input to the AND gate. AND gates, AND gate outputs are also connected as inputs to the OR array with the fuses. We are obtaining your outputs from the programmable OR array. Whereas in programmable array logic, so you're going to transmit the inputs so through the programmable connections to the array of AND gates, and outputs of AND gates are connected to the fixed OR arrays. So here the inputs are not programmable, so only the outputs are obtained from the fixed OR array in your PAL. Now, so we will let me move to your PLA. So here PLD is a programmable arrays of your AND as well as your OR gates. So now these OR gates, OR array, it consists of an OR gates which are connected using your programmable matrix with the fusible links. And here we are going to represent that programmable connection with a cross point on your intersection of your rows and columns. Whereas the AND arrays consists of your AND gates. So where these are also connected using a programmable matrix with a fusible connection. Each cross point indicates so the programmable connection. The absence of cross point indicates here no connection between that input line to the input of your AND array. Next, let me see here. So these are unprogrammable OR array. So where all the inputs complemented and uncomplemented are connected to the input of your OR gate as one of the input. So the second input is also connected. A bar, B bar are connected with the fusible links. So this is the second gate in this OR array. So these are also inputs are transmitted if your OR array is programmable. So hence it is all the inputs are transferred with the or connected with the fusible link. So the vertical lines indicates your inputs of your function, and the horizontal lines indicates your input lines of your OR gate. So now unprogrammed will have your all the inputs are connected with the fusible links to the input of your OR gate. So upon programming, in order to obtain your output from your first OR gate x1, so only I need to have your A and B. So hence I'm going to blown that fuses of your A bar connection along with your here the second input must be your B. So here only I'll connect A on your first line. So A bar fusible link is diffused as well as B is also diffused. So B bar is also blown. So in the same manner, in the second input, only I need to have B. B variable must be connected on your second input, since I want the operation from your first OR gate is A or of B. So first input is A is connected, and the second input line B is connected, and the remaining three input connections are blown. So this blowing fuses are called as programming. So with that, so we can obtain your required summation with the given variables or of your given two variables A or of B. Next, x2 will give you the summation of your complementary variables A bar and B bar. So on your first input line, we will not touch your A bar, so fusible link, but we will blown that fuse of your A along with B and B bar. Next, the second term is B bar, so only we keep that fuse which is B bar is connected onto the input line, and the remaining three inputs which are A bar, B and are blown here. So after programming, the second OR gate will give you the output. So first input is A bar is connected, the second input is B bar is connected. So using an OR gate where we are taking the summation of A bar and B bar. Next, third AND gate will have to take the summation of A or of B bar. So first input only A is fuse is connected. The remaining three, A bar and B as well as B bar, are blown here, and your second input of third OR gate. So where B bar only left with that fuse, and the remaining inputs which A bar, B are blown here. When you blow this, that missing connection would leads to not connected that input to the input of your OR gate. So X3 now it is connected with A along with B bar. So hence the third OR gate will generate the summation of AR of B bar. The same manner you can also program your AND array inputs. So by connecting each input uncomplemented and complemented variables onto the inputs of your AND gates. So initially here we have only two variables. So if I consider your complemented also, so four possibilities. So we have here, and here each AND array is having two inputs. So hence here four input variables. So complemented and two only we have, but we are also considering the complemented inputs. Hence, so each AND gate is having eight interlinks or eight programmable connection with the inputs. So all the three AND gates are having your eight programmable connection. Now, so before your programming, so these are the intact connections of your AND array. So programmable AND array inputs, whereas after programming, so if you wanted to implement a few functions of first AND gate, if you wanted to generate the product of AB, so on your first line I have to leave your A programmable connection, and the remaining A bar, B bar must be blown. So the second input line, so B must be as it is with the fusible link is connected. The remaining fuses are blown. So blown fuse means, so if you transfer a high voltage on this particular line of your input, so that fuse will be blown. So the diffused fuse is storing a logical 0. So hence this B bar is not connected. So there was no connection between the row and column, that indicates that a particular input is not connected. So A bar is not connected, B bar is not connected, along with E is also not connected on your second input of your first AND gate. So where only the A and B is connected on your first AND gate, so it implements the product of your AB. So to implement your A bar, B bar, only we have to leave the programmable connections of A bar on your first input line, B bar on your second input line. The remaining all the connections are blown here. So then it can implement your product of the complementary variables of A bar, B. And the third product term is if you wanted to implement A or of A and of B bar. So first input on your first input line, A must be left with fuse and the remaining all will be blown. So on your second input line, B bar must be left alone and remaining all the input programmable connections are blown here. So with that, so this third AND gate will give you the product of your A bar B. So this is the way, so how to connect your programmable inputs at your AND gate as well as your OR gates. So so this is another way of connecting your programmable connection. So as I have taken the three input variables on this OR gate. So all are linked. So hence it implements AR of BR of C. So this is multiple input OR gate. So this symbol is rewrite with a single input line and with this vertical lines. So vertical lines are the intersection point of your vertical line and your horizontal line, and with the specified input variables which will represent there was a connection between the input variable and the input of your OR gate. Hence here, so this cross mark indicates A is connected as one input, B is connected as a second input, C is connected as your third input. And since it is an OR gate, so it can implement the summation of your three input variables connected, which are AR of BR of C. In the next diagram, so here this is the initial state without programming. So if I want to implement a function which is AR of B, then I need to blow that fuse which is connected on C. So blown fuse indicates there was no connection between the C variable and its input of your OR gate. So the third input is not connected with the C. So that not connected C input variable is represented without intersection point on your C, on your vertical line of your C, along with your input line of your R. So the absence of your cross mark indicates there was no connection between the input variable C with the input of your OR gate. Hence only the input variables which are connected is here A and B. So the output function obtained from this OR gate is AR of B. Now let me move to your another AND gate programmable connection. So fusible links. So before your programming, so which implement the product of ABC, and here also. So if they are connected, so then we have to make sure to put the cross marks over there. So that cross mark indicates that particular input variable is connected as one of the input of your AND gate. Since all these three are connected, so it will implement your ABC. But here, when you program it in order to obtain your B, so you have to blown the C. So C input fuse must be blown. When you have blown that fuse of C variable, so there was no connection between that C variable to the input of your AND gate. Hence, it will only implement the product of your first given two variables, which are A, B. So like this, so you can program your OR array as well as your AND array. So really similar as like your PROM, only the difference here is you don't have your any decoder like your PROM. So decoder, if you have, each decoder output will be one minterm, so which is considered as a fixed AND array, whereas here in your programmable logic array, so you have an array of AND gates which are all inputs of your AND gates are programmable, and there was your OR inputs are also programmable. So inputs which are transferred to the input of your AND gates are programmable, as well as outputs of your AND gates which are connected as the inputs to the OR gate is also programmable, and we obtain your outputs from your OR gates outputs. So this is your actual basic principle of your PLA. So both inputs, your AND arrays as well as your OR arrays are programmable. So we were going to obtain your outputs. So in your, so while you are implementing your functions which are in sum of product form, so we can obtain the outputs from your programmable OR gate outputs. So now here we can obtain your both complement function as well as your uncomplement functions also. So uncomplemented functions also using your exclusive OR gate. If you connect your X exclusive OR of 1, so which will give you the output which is X bar, complement of X. If you transfer your X input along with the 0 input on exclusive OR gate, so it will implement uncomplemented function. So X exclusive OR of 0 is equal to X, X exclusive OR of X 1 is equal to X bar. So now let me take a one simple example. So F1 is equal to AB bar plus AC plus A bar BC bar. F2 is equal to AC plus BC bar BC whole bar. So in order to implement this function, so this function is a complement function. So F2 is defined like a complement function. F1 is defined like a true function. So it is an uncomplemented function. So now we have to use the programming table which is called as your PLA programming table. In this programming table, first column deals with all the product terms of your given two functions, and the second column we have your numbering of your how many product terms are there in your given two function, and in the third column you will have your given inputs, so where you wanted to with which inputs you have to implement your functions, that inputs are represented here, and your outputs, so those outputs which are in uncomplemented which are represented with the T, and if it is complemented then that are represented with the F2 of C. So here I have been given AB bar AC plus A bar B C bar. So now when you compare this, so AC is common variable, so only one product term is enough for implementing this two functions with the four product terms. So AC is common, since AC is common, so AC is one product term, AB bar is the second product term, BC is the third product term, and A bar BC bar is the fourth product term. So hence we are taken only four product terms here. So in AB bar, A become logic 1, B is a 0 value, hence the product term is AB bar. So this belongs to the function F1. So AB bar, hence function AB bar is present in your PLA So hence we represented f1 is equal to 1. So AC is present in your f1 function along with f2 function. So f2 function value is having a product term of AC's complement function. So hence we put a logical one on that column. So whereas here AC is A value is 1, C value is 1. So BC product term B value is 1, C value is 1, and you doesn't have your A value. Next, F1 doesn't have your BC, so hence we are represented with a blank. So where BC is present in your function F2, so hence we represented your F2 of complement with your logical one. Next, A bar, B, C bar is your third product term, so the fourth product term that will be available in your F1 only. So where A value, C value is 0, B value is 1, and F1 of T become logical one. So now here I have taken one buffer and one complement. So this bubble will give you the complement of the variable, the second line which will give you the uncomplemented variable. So now we have taken three input variables, hence so the bubble line will be the complemented variable. The absence of bubble indicates here, or the buffer we call this as a, which is here A value. So in order to implement this PLA table, so we require 4 number of AND gates. So and those 4 number of AND gates which implement one of the product term. So each AND gate can implement one of the product term. Now first AND gate, if I wanted to have AB bar, so I need to put a cross mark on your A along with B bar. Hence we put that two cross marks on this. So because inputs of your AND gates is programmable, so it will give you the AB bar product term. Since we connected only A as well as your B bar. So second product term is having only AC value. So hence we cross that AC value along with the line of your C. So now the second AND gate which will implement your product term of AC. Next, third one will give you the BC value. So B along with C, we crossed it. So the third AND gate will give you the product of your BC. Next, last one is having three inputs which are A bar, B, C bar. So A bar, C bar as well as B bar and sorry B, so along with C and A bar. So A bar, B, C bar. So hence it will give the product of A bar, B and C bar. A bar, B, C bar. Now function 1. So function 1 is having here all the three product terms which are A bar, B, B, C. So A bar, A, B bar, AC it is having along with A bar, B, C. So which is true value, so hence it is connected, that second input of exclusive OR gate is connected to logical 0, output of this OR gate is connected to the one of the input of your exclusive OR. So now it will give you the product of your, so F1 is now F1 exclusive OR of 0 which will get your true value, where F2 is a complement one. So hence it has been connected only the two product terms which are AC and BC, and in order to obtain the complement, so which is a complement value F2, so hence here we put that logical ones on your AC and BC. So the second input is connected to logical one, so which implements the complement of your AC plus BC whole bar. So F2 is implemented by taking the output from this second exclusive OR gate. That second exclusive OR gate input is connected, one input is connected with the logic 1, other input is connected from the output of your OR gate. OR gate output is, here we obtain BC OR of your AC. So now upon connecting this BC OR of AC exclusive OR of 1, we obtain your complement of AC OR of BC. So like this we are going to implement your given function using your PLAs. In the next class we are going to connect your or implement your Boolean functions using PALs. Thank you.